Tonight, we're going to talk about solving space junk. On December 4th, I've got an update on photonic propulsion, specifically on photonic propulsion. We're not going to be talking about EM drives. And then on Saturday, December 11th, we'll be doing our presentation on the James Webb Space Telescope, along with our subject matter expert from the Space Telescope Science Institute. There will be no session on Saturday, December 25th or on Saturday, January 1st. So good evening. Tonight we're going to be talking about solving space junk. This is current in the news as of some debris that was created by an anti-satellite missile that is directly affecting the International Space Station and the humans that live aboard it. There are tens of thousands of things in orbit currently about the Earth, and a week ago we got another 50 some odd courtesy of SpaceX Starlink. So they're now closing on 2,000 satellites in their system. The quantity itself is not really the problem because there's plenty of space in space to fit them all. We're not having any close encounters of things that we have in known orbits because the orbits have defined separations that prevent such things. But what we have is a lot of spent stuff that I'll just call junk. And we also have a lot of debris. And the debris is from very tiny bits of stuff. Every time we launch stuff up there, the junk pile grows, so to speak. Satellites that we send up there have a programmed lifespan of maybe about 5 years. That's their static container of fuel for keeping themselves in their orbital position. When you put stuff up in orbit, it doesn't stay there. It stays approximately there. But if you expect a satellite to always be in the same spot, you need to occasionally do things. Sometimes it's just orientation, which you can use a momentum wheel or a gyroscope to adjust that. But if you have to slide yourself sort of left, right, down lower or up higher, you generally have to use F equals ma and some kind of propulsion system to do that by today's rocket propulsion definition. Even if it's something that's being launched to the moon, there are boosters that might remain in high Earth orbit, that might go into elliptical orbit, that might be there for a long time. I believe that there is one of the Apollo boosters still in orbit about the Earth. So you put it in the right orbit, it can last for 100+ years easily. So these pieces are moving in orbit, which means they're moving at high velocity, greater than 10,000 miles an hour or 16,000 kilometers per hour, potentially in opposing directions, which doubles the collision force. Not only does this junk present a collision hazard, but if you have, let's say, a satellite that can no longer control its positioning, and it happens to be in a valuable geostationary slot in orbit, and you want to put up its replacement, how do you get it out of there? Because it's occupying valuable real estate. You can't put anything in there to replace it if it won't move or it doesn't have any fuel to move. Stuff that's in 8 orbits cross other orbits. So if you have something that's politely in a circular orbit, and then you've got something that's in a long elliptical orbit, those orbits can occasionally cross, and if you're in the wrong place at the wrong time, you can have a collision. Sometimes things that are in good orbits, in order for them to be well behaved, have to dodge things that can't control their orbit that are in bad orbits. And that's one of the things that these Starlink satellites do have from SpaceX is they have their own ion thrusters, which they can use to not only keep themselves in their proper orbit, but can get out of the way of things. And they actually have onboard radar that allows them to detect it on an ad hoc basis. It doesn't have to be, get out of the way, something's coming, as told by the Earth. It can be, I've detected something on my orbital path, I'm going to move a little bit. And they can do that. So far, all of the mitigations or solutions to this have been incremental. I don't know if you read the article this week, but there is a new form of ion propulsion that instead of using xenon or krypton, actually uses iodine or iodine, but it uses it as a solid that it heats to a liquid and then ionizes the liquid iodine to use it as an ion propulsion engine. And because the iodine is solid, you can ship up a higher density brick of iodine than you can a pressurized gas spherical chamber of a xenon or a krypton. And also iodine is more prevalent, so it's cheaper. So they're looking at using iodine for ion propulsion in long duration missions. They haven't yet said about using it in satellite propulsion because iodine in that formula is actually toxic. So you don't want that becoming a fuzz around the earth of poisonous iodine. The iodine you use in hospitals is actually a chemical compound. It's not pure iodine. There have been discussions about setting up fuel reserves purposefully to deorbit low Earth orbiting satellites. And I know that the SpaceX Starlink satellites do have this. They reserve a certain amount of their fixed fuel supply as end of life, push yourself back down and in a controlled manner, burn yourself up over the Pacific Ocean, the Atlantic Ocean, or Siberia. And the materials that the satellites are made of are specifically designed to more effectively burn themselves up. So they're being a good neighbor. But what happens when you have a failure of components on board the satellite and it's a malfunctioning satellite? If it gets an engine stuck in the on position, who knows what orbit it will wind up in by the time it runs out of fuel. If it can't make its engines fire or it loses radio communication with the Earth, how do you get it to deorbit itself? You can't. You need something else. And what you need is something that can be a very long-lasting, very inexpensive solution to deorbit things. And it needs to work even if the thing you're trying to deorbit is broken. So the first possible cure that is being promoted is what is known as AKMs, or Apogee kick motors. So if you've spent tens of millions of dollars for a geostationary satellite and you want to give it another 5 to 10 years of life, if it only cost you $2 million to put a rather dumb kick motor up into geostationary orbit to grab a hold of the back end of the satellite and push it up to a higher orbit, you know, and give it some fuel for another 5 to 10 years, it may be well worth it given the cost of the satellite and what it, you know, how much it costs to put it up there. So that's an Apogee kick motor. But it only works on well-behaved satellites, and those satellites that are either prepared to receive a docking booster or ones that don't mind their rocket bell on the bottom being grabbed by one of these boosters. But launch delays are always inevitable. If you send up your AKM too late and it starts to get out of orbit and run into things before you can get your AKM boosted, you may not have a chance. And it'll only do this for about 5 to maybe at most 10 years because it's got the same fuel supply limit the original satellite had. And it doesn't work on satellites you got to go chase down because you won't have enough fuel on your AKM to chase it down if it's in a long elliptical orbit. You won't catch up with it. And it doesn't work on satellites or debris fields from explosions like anti-satellite missiles. Plus, it's a very expensive solution and it only works one time for one satellite. Well, if these only work one at a time and you say, I want to extend it another 10 years, and you send up another AKM, can you, daisy chain these multiple on the back of the satellite? Or will that change the center of gravity of the satellite and now it won't operate properly? Well, I'm going to take off the spent AKM. What do you do with that? You just created junk. And I'll put on the new AKM. What do you do with the one you just let go of? Well, if it's empty, obviously it's not coming back down. And even if it's not empty, you're in geostationary orbit. It takes a lot of fuel to push you all the way back down to deorbit you. So we need a better solution. So that's not really that great of a cure. How about space tugs? I've seen this in science fiction and people mentioning space tugs. This is same thing as an Apogee kick motor, but at a different altitude. But it's going to have a net or a grappler, and it's going to drag the satellite back down and burn it up. Well, when you grab the satellite, you're going to change your orbital characteristics because you're now more massive. So are you going to be able to, in a controlled manner, do this? And if it's a satellite that's on an elliptical orbit, you're not going to have the fuel to chase it down. And if you're trying to do this for an exploded satellite, I'm sorry, your net's not going to be fine enough mesh to carry all the small pieces, and you're not going to chase down a large, sparse cloud of pieces. It's just impractical. And when you do this, one space tug dragging down one satellite is a one-to-one, and it's very expensive. You need something that's going to work longer and with less of a financial penalty per deorbit. And then there's the capture and bring it home for refurbishment. This is one of the things touted as a capability of the space shuttle, is that it would be able to go up, open up the doors, deploy a satellite, and if they ever had to bring the satellite back home because it was malfunctioning, they could go up, open up the doors, use the arm, grab the satellite, put it in the cargo bay, and then bring the satellite back home. I think they did that once as a proof of concept and never did it again. I think that when you bring back something that massive, it tends to change the characteristics of the shuttle. For landing, there were a number of times that the shuttle landed rather heavy because of atmosphere and wind and things like that. But the idea is you send something up that goes up there and removes all the big bits from the satellite, solar panels, it just kind of flips those off and they go somewhere. They just become debris. Or if it's got a giant parabolic dish antenna, it clips that off. So you can get just the electronic meat of the satellite you're trying to bring back for refurbishment, not to burn it up. Again, doesn't work for things that are in uncontrolled or highly elliptical orbits. It doesn't work for really heavy satellites in geostationary orbit because you won't have the fuel to get up there and enough fuel to get all the way back. It doesn't work for exploded satellites or sparse debris fields because you can't collect all the pieces. And once again, it's very expensive to send it up, and it's a one-to-one. You go up, you grab it, you come back down. Is it a refurbishable launch vehicle to do it again? It would be very expensive, as we found with the shuttle. Now, maybe if SpaceX, if their spacecraft ever, grows its alligator nose to like open up the nose like that James Bond movie did and grab the satellite and then bring it back down, maybe then. But I think they haven't thought about center of gravity because that would be on the nose of it, tons of satellite. And I think these kinds of things would only be deployed if there's heavy international pressure to spend the money. Otherwise, you get a financial penalty for leaving garbage in the neighborhood. And then here's the one that came up this week. Well, we'll just shoot it down. Not a good idea. It's just nonsense. It results in either lots of pieces if it explodes in a behaved manner, but most likely it's going to explode in an unbehaved manner, in which case various sized debris are going to go out in a cloud-shaped, dual-lobe, spherical thing that's it's just going to be horrible. So not a good idea. Now, Russia did have a good point that they did it, but we did it first. So the US was the first to do this back during the Star Wars program to prove we could shoot down things that were in orbit. Yep, we did it first. Then the Chinese did it, and now the Russians have done it. Apparently, every major nation that has launch capability has to prove they can blow up satellite.
That's stupid.
It's stupid. It's military nonsense. If they really just wanted to incapacitate a satellite, a laser or an electromagnetic field would work just fine. And it wouldn't blow up the satellite. And it probably wouldn't do much to its orbit. But I have a thought. We know that radiation reflective pressure does work. It can move things. Otherwise, solar sails wouldn't work. We know that lasers are a great way to slowly decelerate things like, I don't know, molecules when you're trying to super cool things. How about using a laser to deorbit debris? Now, you could position a laser above the targets and then point them downward at the targets to not vaporize them or burn them up or ablate them away, just to nudge them. And you would do this multiple passes. If you're higher in orbit, to something lower, the thing that's lower is going to go around several times to your slowly going around once. So as it went around, you could zap it, zap it, zap it, zap it, and slowly push it down. And by doing that, you'd have a controlled descent. Now for junk, instead of focusing it down to the size of the satellite, make it a broader beam and just do it more often. It shouldn't take more than a few kilowatts if you're in orbit above it to do that. So not, something that's going to be harmful to us here on Earth. If you had a laser that was in the near ultraviolet but not into ultraviolet wavelength range, that would transfer maximum momentum without causing difficulties in your focusing and tracking mechanisms. And since you're towards UV, it would be very difficult to get a beam that's widely dispersed all the way down to the Earth, because the water vapor in the atmosphere would scatter that field and not make it back down. It's why you get burned by a certain wavelength of ultraviolet light, but not the horrible stuff. So UVA, UVB, UVC doesn't make it down. So you would need to focus the beam to something that's small enough to the satellite. And we can do that with a laser, but you need to focus it. And if you want to focus a laser, you're going to need mirror and you're going to need lens. And so you have to make sure that those work and are compatible with whatever wavelength of laser you pick. You put the laser slightly above geostationary orbit. So it would actually be orbiting slowly, slower than the rotation of the Earth, so you could catch different kinds of orbits. Anything low to geo, you could focus down on them, and anything that was elliptical, every time it came by for a pass, you could beam at it, and the Earth would be rotating underneath you, so you would have more opportunities to hit all the stuff below you. If you were to go and say, well, why don't we just use the shortest wavelength possible? Why not deep UV, like UVC, or X-rays or gamma rays? Mirrors and lenses that are made out of glass are fairly cheap and easy to come by. Once you start getting into deep UV, X-rays or gamma rays, photons behave differently. Let's say you wanted to use deep UV. You couldn't use glass because glass blocks deep UV, blocks UVC. You have to use different kinds of materials in order to transfer UVC through your lens. So let's forget UVC. Well, what about X-rays? Shiny mirrors and glass lenses do not work with X-rays. You have to use magnetic field coils. And that gets to be much heavier to launch into space than a mirror or a glass lens. And gamma is just way too much energy for even that. The best you can do with gamma is you have dense blocks that absorb what you don't want scattered in your field. So yeah, we have X-ray satellites that can observe in X-ray. We have gamma radiation satellites that can observe in gamma, but those are specially designed and they have magnetic field coils to direct the X-rays, and they have dense blocks that act as kind of a channel or a waveguide for the gamma radiation. So what we should use is something that is not quite UV, and my recommendation is either royal blue, which is at 440 nanometers, or closer to UV but still can be bounced by glass mirrors and focused by glass lenses, which is violet at 415 nanometers. When you get down into the 405 to 400 nanometer, you start needing special materials if you want to reflect or focus. And I know that the mirrors become what they call cold mirrors, and they're gold-plated mirrors. So that makes them far more expensive. So what would the process be for deorbiting something? Well, you would gradually nudge it down. You're not going to vaporize it or ablate it away. So you put this in orbit, and if it's in a nice higher than geo orbit, it could be up there for 100+ years. If you give it a little bit of a fuel tank and some large solar panels, it would have more than enough power to do this for quite a long time. You would give it a list of things to deorbit. satellites, debris fields, and every time the object passed beneath it, it would very quickly switch the beam off and on to give it that shotgun effect to push on it, and it would slowly come down. Now, if the object is rotating, if you're rotating this way and the object's coming at you this way, you want to angle the beam so that it degrades. It creates a negative delta V to change the orbit so it starts coming down. And if it's facing the other way, then you probably want to hit it on the backside to change its orbit, to change the delta V in the other direction. Because remember, if you're going faster, you're in a lower orbit than if you're going slower. It's counterintuitive, but that's just orbital mechanics. As you nudge it down further, you want to make sure that if there's something at a higher orbit that passes between your beam source and the thing you're targeting, you have the beam switched off. You don't want to inadvertently, add a little reflective pressure to deorbit something that's unintended. So you have to be switching it off and on very quickly. You'd get a schedule of the orbits. You'd say what you're going to be taking down, and you just over time slowly degrade its orbit until the atmospheric friction starts to reduce it faster. Another thing you can think about doing is if you have something that's uncontrolled, that's got a spin to it, you can actually hit the beam on it to retard the spin and stabilize it. So if you have a otherwise functional spacecraft or satellite that is just spinning and you can't communicate with it, if you can stabilize it so it's no longer spinning, you might regain control of the satellite. But then again, shortly before it starts to deorbit and burn up, if you could use the laser to kick it, to spin it, it would make the burn up more efficient. This is a little bit of a numerology here, but if you were to calculate the altitude versus orbital speed distance versus the angular degrees per second and the orbital period, this would give you an idea of how complex it would be to have a laser go to and track a target. If you're in geostationary plus orbit, your orbital period would be like 26 hours or greater than a day. If you're trying to deorbit something that's on low Earth orbit, it's going to go by every 2 hours. So you have plenty of opportunity to hit it many times in a single day. But you need to make sure you don't hit anything on the way down. And you need to make sure that you kind of slam it a couple of times every time you have the opportunity to hit it. So you're going to be switching the beam rather quickly. A better place to park it, instead of high geostationary, would be, we've discussed Lagrange points. If you remember, the James Webb Space Telescope is going to be at the L2 point. There's another point called the L1 point, a very bad place to put your infrared telescope, because one side of it would always be facing the sun, and the other side of it would always be facing the Earth-Moon system. This would be an excellent place to put the laser, because it would always have the sun at its back, so it could always have the solar panels pointing at the sun without having to tilt them as you orbit the Earth. The Earth would be rotating beneath it, and you could target things in any orbit. And another benefit would be, gee, the moon orbits below you as well. So once we start putting more junk in orbit about the moon, as we start, launching and landing things at the moon is smaller diameter, so the orbital station's opportunities are reduced. So you want to get rid of the junk. Well, what are you going to do with the junk? Well, the moon doesn't have much in the way of atmosphere, but it does have gravity. So you'll have to push a little harder in order to deorbit things orbiting the moon. But, putting the laser at L1 would be very good. And if you put multiple lasers on board, it could actually deorbit multiple things simultaneously. Now, if you put it exactly at L1, then the antennas on the Earth wanting to talk to the satellite can't, because the sun's in the way. So you might want to put it in one of those funky halo orbits, so it orbits about L1, but that would cost a lot of fuel. So put it L1, and we'll just use the TDRS satellites in geostationary orbit about the Earth as relay satellites to communicate with it. We won't try and point the radio antennas directly at the satellite. And since we're not doing imaging with this satellite, the data rate is likely to be for scheduling and status communication. So we could use an S-band transmitter. You wouldn't need to use that high capacity X-band transmitter like the Webb is using. If you want to track a satellite that you're trying to shoot down, if you're in orbit about the Earth, your imager would have to work in both infrared and visual. But if you're always at L1, you've always got the sun at your back, and anything you're trying to target would always be in sunlight. If you're using cameras for targeting, they would always give you a nice reflective view of your target. Same thing would be true if you're trying to take out orbital debris about the moon. You would catch the moon as it's orbiting on the sun side. So there's benefits to being at L1. How much beam power are you going to need? Well, as we all know, the amount of flux or photon density per square area is going to be different as the distance increases. So at L1, you may need a megawatt class laser. You're obviously going to need larger mirrors and lenses and a longer focal length to make the beam smaller by the time it hits a low Earth orbiting satellite. So maybe we start at medium Earth orbit where there aren't many satellites, and we do a proof of concept launch with a Falcon 9. So once we've proven that this is beneficial, and maybe even SpaceX in conjunction with NASA would like to fund something like this. Now, once it's been proven technology, if they want to put something at L1, it would benefit all nations on the Earth. You would no longer have to take down your own satellites. This could take them down. Maybe there would be an international consortium that could be funded by either contributions from various nations or a service fee to take down your satellite based upon, is it geostationary, is it low Earth orbiting, is it under control, not under control, is it a Molniya orbit, is it a nice circular orbit? Ask all those things and then charge the appropriate fee. But I would say an international consortium makes sense to do this at L1 because it's going to cost more to get it out there. And do ask China and Russia. I think it's worth their while to do it. Avoiding this satellite being its own example of enemy, you want to use redundant everything so that the thing that you put at L1 stays there for a long, long time. If you are stuck with fixed capacity liquid fuels and momentum wheels, this thing is only going to last about 10 years. So you need to start thinking about maybe ion propulsion, scavenging solar wind instead of having a fixed tank of xenon or krypton or iodine. So you got to move away from that because we want this thing to last 50 years. So you have to have redundancy. You might want multiple lasers on board so that you could simultaneously take down multiple satellites. Or you could, if the laser is really powerful, you might want to have it disperse heat into space before firing again. So that way you could sort of a Gatling gun style to avoid the barrel melting. You have multiple barrels. Or you could have multiple lasers fire on the same target simultaneously. So, conclusions. Earth orbiting space junk is an increasing problem. It's not a matter of how much space we have to put legitimate things up there. It's the junk. It's not a can to be constantly kicked down the road as we create new junk, ignore existing junk, park geostationary satellites in a less expensive orbit. In the absence of any international regulation to clean up your junk, organizations and governments that launch junk are just not going to deal with it. And blowing up stuff just makes more uncontrollable junk. Space tugs and Apogee kick motors just are not an effective solution, and they're too expensive and they don't work on debris fields. Lasers can push things. Let's use them. A couple of kilowatts in geostationary should be sufficient. Not quite ultraviolet. As the beam distance increases, you need something to narrow it down smaller. But once it gets below low Earth orbit, it's going to be wide enough, diverged or dispersed or diffracted, that it's going to be safe for aircraft. You need to be able to task the beam to multiple satellites at multiple times so that you can just slowly push them down. Parking it at L1 makes sense. There's a lot of benefits to doing that, but it's going to require a more powerful laser due to the increased distance to target So plan it out. But you know, I did not see this on the decadal survey the U.S. just recently published as, what are you going to do about junk? Everybody just said, we're going to launch more junk. Okay, and I've got a couple of links in the presentation for if you need more information on how UVC is blocked by the Earth's atmosphere, the benefits of an L1 point. If you want to go back and say, if I want to orbit something at this altitude above the Earth, how fast would it have to be going? So there's actually an orbital calculator for doing that. And why shooting things down does not make sense. So, any comments or questions?
What is the name of the syndrome? They say that one starts to bump the other, who breaks apart and destroy all the satellites. Kessler or Chrysler, something like that.
Kessler.
Kessler syndrome, yes.
Kessler syndrome, yes. If you think about nuclear fission, the idea is you create a chain reaction. You know, one thing hits another thing, which creates two things, which creates more things to hit other things. And the Kessler syndrome is if we have a large enough collision creating a large enough sphere of debris, that debris will interact with other things in orbit, and therefore you'll have a cascading effect. You'll have a chain reaction, which will create a debris cloud around the Earth, making Earth orbit no longer viable for satellites or spacecraft. This is a worst case scenario. There is a probability it could happen, but it's a low probability at the moment.
For now.
At the moment. We keep putting more things up there, the probability goes up. We keep leaving more junk up there, the probability goes up. We keep doing stupid like blowing up satellites, the probability goes up higher, faster. Satellites in orbit, that's fine, I'm okay with that. But clean up your junk and don't blow it up.
Any questions?
Questions? Comments?
A comment.
Yes, go ahead.
All right, question, I guess. I don't, I hear you saying that you're not opposed to them sending more stuff up there, but everything they send up there becomes junk eventually.
No, if you look at what SpaceX has done with their Starlink satellites, they have a purposed lifespan of 5 years at most, and they've already sent down a single-digit number of satellites on purpose to prove that their calculations are correct. So as they orbit first-generation satellites, each one of those satellites has a planned lifespan and deorbiting. They have a couple of the satellites that never made it to their target altitude, and I think they need a solution for that. Now, whether it's a space tug or a laser pushing them back down, they need a solution for that problem. But as far as corporations that put stuff up, that police their stuff, I think that SpaceX is currently ahead of the pack. There are no commercial satellite vendors that put things into geostationary orbit that have ever brought any of their satellites back down. They've all just parked them in another slot in geostationary orbit at the same altitude, just, we'll do it over the Pacific or over the Atlantic or over Siberia, all the prime spots above all the continents where there are lots of customers with antennas like, satellite TV receivers. Well, that's the prime real estate. They want to get the old satellites out of there. And that's where the Apogee kick motor concept and the space tug concept came in, is they need to get those out because it's not the satellite that they're removing that is cost effective to reuse. It's the slot that the dead or misbehaving satellite is in. They want to get it out of that real estate, either bring it back down or put it in some other spot that's less expensive real estate. I think we're probably many tens of thousands of satellites away from, kind of running out of real estate. But I think that all the satellites need to police themselves.
They are taking up space in those slots, right? I mean, even if it's a tiny little space, we can see that they keep doing that. They're going to take up the whole parking lot.
There's a long way to taking up the parking lot. SpaceX has already filed with the FAA to make their satellites about 100 kilometers lower to reduce the transit delay of the radio signals, which would make them deorbit faster. If you've seen the amount of time it takes a Starlink satellite to go from launch to being in station and where they expect it to be, it takes several months at their low performance propulsion system to get them up to where they need to be. So I don't expect Starlink satellites to push anything else down. Also, they can't get up to geostationary. That's quite a bit higher in orbit than they have the total propulsion for. I think that the cost effectiveness of trying to take something that you pushed up to geostationary orbit and getting it all the way back down from geostationary orbit in a controlled manner, I think that commercial vendors will just find a way to exert political pressure where they don't have to do that, because that's just going to be too expensive. You have to put too much hypergolic fuel on board the spacecraft, which increases its explosion potential.
So am I correct in thinking that most of our junk is higher than where SpaceX is going to be?
No, it's all over the place. There's junk at all altitudes and in all orbital planes. So depending upon the size of it, if it's something large that's in a controlled trajectory, like a rocket booster, it's going to be up there for 100 plus years. We'll just make sure that nothing else gets that entire orbit. If it's on an inclined orbit, same thing. If it's a debris field, well, we're not going to put anything in the debris field, but as the debris field itself is orbiting, that creates a swath that we can't put anything in. We need a long-term solution for the problem, and we need the ability for it to be effective at both individual whole objects of very large size rocket boosters all the way down to very sparse debris fields and push all that down. That's why I came up with the solution is identify a problem it doesn't solve. I couldn't think of any.
Say that again?
You have to be able to deorbit very large things like boosters. You have to be able to deorbit very large things in geostationary orbit like communication satellites. You have to be able to deorbit things that are not controlled because they malfunction. They're on a weird orbit. You have to be able to collectively bring down debris fields that can be sparse, that can be very spread out. And you can do that with a beam that you repeatedly push on the entire debris field, kind of like shining a big bright light on it. You can't do that with an Apogee kick motor or a Tug.
Okay, so now when I talk about one time, I'll say something like you'll say about junk, and you'll say it's all over the place, and it doesn't sound like it's very far away from each other. And then I say something, and then it's like they're all too close or they're all too far away. So my understanding right now is that there is a lot of junk up there, but it's not very close to each other. And so there's a big problem on sending something up there to do one job and then on its way back to pick up something because it won't necessarily be in the same area the junk is.
Correct. And think of it like if I throw a football into the air and I want you to take out that football, it's one fairly large thing. Now it's a celebration and you've got a confetti gun and you blow off a load of confetti. I want you to pick up every piece of confetti before it hits the ground. Yeah. You've got to solve both of those problems.
But one of the things is that if there's confetti going up in the air, and you have an area that's been designated to have that, then you send in the crew to clean it up because you've been prepared for it. But we haven't been prepared for this kind of junk up there to have to bring it down or clean it up. It's sort of like the ocean also. It's like, there was a big ocean and people say, oh, you can throw that in the ocean because, hey, it's a big ocean. But it's not that big when you get started, and it seems to me if we could start now and do something. But what I hear you saying is that we shouldn't focus on what's up there so much as to focus on making sure we don't make any more junk.
I think you should focus on both of them. You've got to eliminate the junk that's already up there, the big stuff, the sparse, dispersed stuff, you've got to have a solution for both of those. And you've got to make sure that anything you send up now, that you give it enough fuel so that it has an end of life deorbiting capability. And if you can't do that, then you should be paying an international fee for someone else to clean up your mess.
Now, is that proposed at this current time, or are people paying attention to it?
The
No,
UN,
some comment. There is like few people who worry about that, but they look at people who says that like tree huggers, kind of thing. It's like, it's big enough, don't worry about it. Like the analogy that you did with the ocean, so it's just perfect. And same thing is for spacecraft.
well, we already know that there are certain industries that count upon government to clean up behind them at no cost to them.
At least he's making us think about it, though, too, about what's going on.
And there's certain things he can do something about, even if he contributes billions to it, like changing from internal combustion engine to electric vehicles. He can make that happen. But, solar power in your home, even he's had a tough time making that effective. He's doing
But he's sending up, you're saying the skylight, that they are sending them up with the idea that they won't be junk up there. And that's a very good step in
Yeah.
showing other people that this can be done. Because a lot of times people just say, oh, we can't do anything about it. Well, that's
No,
not true.
he's doing something about it. But you also got to think about the method to his madness, which is if the US government is assigning him certain orbital slots and his satellite is in that slot, and that's a generation 1.0 satellite, what's the easiest way for him to get a generation 2 satellite into that position? For him to not give up the position and just deorbit the first one and put the second generation in its place. He's reusing his own orbital positions.
So he was motivated.
He's recycling. He's
Right.
deorbiting. He's deorbiting it. He's creating the spacecraft with more effectively, burned up things with less hazardous waste on them. And he's reusing the slots he's been given. So,
Right. And you're telling me he was motivated to think about how his slots are being used and to not do junk.
I think it was
But
more about how do I reuse the slots? I'm not going to get more. Well, if we deorbit them and we deorbit them so they're not toxic, they're more likely to let us reuse our slots. So I think he started with once this satellite's no longer useful, how do we get the approval to use that same slot? And it's you never give the slot up. So when he talks about his Starlink program may need 40,000 satellites, that's for the duration of the program. He probably needs less than 10,000 satellites to cover the entire Earth. But over the lifespan, over multiple generations, it'll be like 10,000 satellites every 10 years. But they won't be additional, they'll be replacements.
It's good that he's thinking ahead.
Yes.
And that it's good that he's doing that so he can set examples to others.
Yes.
Yeah, it's excellent. Of everything we talked about recycling and what companies are doing and happening, it's the only one that isn't fake.
Yeah. Okay. Done with this presentation? Stop recording?
Yes. Thank you.